Thank you. It's a great pleasure to be here in person. I'm from the Australian National University, which is situated on the ancient and rightful lands of the Ngunnawal traditional owners. My talk is based on work reported in these two publications from 2020 and 2021 with my partner in crime, John Brindley at Leeds University. I actually spoke about some of the work in the 2020 PCCP paper way back at the last in-person NORCAL conference at Athens. I think I talked about some of our preliminary results then. But now I've got more results. And we basically asked two questions, and they are these. Given that the primordial prebiotic environment, wherever and whatever that was, would have been non-uniform and messy and subject to fluctuations? We asked, firstly, was a fluctuating environment necessary for complex prebiotic chemical systems to emerge and persist? And secondly, if so, what might be the optimum variance of such fluctuations? In other words, how messy was just right? So we heard yesterday about Goldilocks conditions. Well, we set up a model system to represent a putative origin of life setting in, hydrothermal porous rock, perhaps. We have this cell with an input flow and an output flow. Very simple model. It's in contact with its environment thermally. So the dashed lines represent thermally conductive walls. So it's a thermodynamic open system. And the environment is at a constant ambient temperature, T sub A. The power input to drive prebiotic reactions cyclically is provided by the hydrogen peroxide thiosulfate redox system, where in this model those reactants are in continuous supply. Now, this is a thermochemical oscillator which has been well known and characterized since the 1970s. You'll find it in the chemical engineering and physical chemistry literature. And in a cell, we get these uniform thermal oscillations. Between about 10 and 50 degrees C, and with a period of a few minutes. So 90 seconds to 3 or 4 minutes. And we've previously used this system to drive small RNA replication, ribozyme action, and polymerization. And those results are reported in various papers, Journal of the Royal Society, Interface, and Astrobiology, and so on. Now, okay, that's all very well, but one thing we do know about the environment that hosted the emergence of life is that it was not, I mentioned the chemical engineering literature, but the environment that hosted the origin of life was not like a chemical engineering lab or any other sort of lab. It was a fluctuating, messy environment. So to simulate these effects, we made this ambient temperature, TA, into a Gaussian quantity, fluctuating randomly about the mean with variance S. We supply the hydrogen peroxide and thiosulfate as before, and we get thermal oscillations in the cell again, but they fluctuate in amplitude and period in response to the input fluctuation. So the oscillations we get in the cell are the output fluctuations. Under the oscillating thermal drive, these form simple vesicles or micelles, and small biopolymers, and feed a primitive metabolism. In different experiments. So there we have, we also supply in the input various simple organics. And in different experiments, we end up with biopolymers and or vesicles and or a simple self-sustaining metabolism. And here, this little sort of Gaussian distribution I've done underneath, I just did it to emphasize that the input thermal fluctuations are normally distributed. And I also want to emphasize that these input fluctuations are macroscopic thermal fluctuations. They are not the fluctuations with energy magnitude KT, where K is Boltzmann's constant and T is the absolute temperature, which are present whether a system is at equilibrium or not. So they are not microscopic thermal fluctuations. They are macroscopic thermal fluctuations. So we have this normally distributed input fluctuation. What does the fluctuation distribution of the output look like? So what does the fluctuation distribution of the thermal oscillation amplitude look like? Well, that's what it looks like. So we ran ultra-long time series to obtain millions and billions of data points, and post-processed the data to extract the fluctuation amplitude and run them out as a histogram. And what we see in that is that normally distributed input fluctuations do not produce normally distributed output fluctuations. So naively, you would expect that a normally distributed input fluctuation would lead to a normally distributed output fluctuation, but it does not. We get this left skewed, right weighted distribution. what does it mean? Well, we've got this significant weight. So this, I said it was right weighted. We've got this significant weight towards larger temperature fluctuations. And this means that on average, the system supports high activation energy biosynthetic reactions over low activation energy degradation reactions. So we're beginning to see how this situation favours structuring, complexity, and persistence in the prebiotic world. Well, okay, what happens if we suppress the thermal oscillations in the cell and run the fluctuating system at a steady state? So instead of the dynamical state, always changing with time, the oscillating state, we run the system at a steady state. It's still highly out of equilibrium because it's a flow-through system, but it's at steady state. We've suppressed the oscillations. And we can do that there's various tricks for doing that. We can do that physically in various ways. Well, we get this opposite distribution. We get this right skewed, left weighted distribution, like a Boltzmann distribution, weighted towards small, low temperature fluctuations. And the large, high temperature fluctuations, which you need for high activation energy synthetic reactions to predominate, occur on average less frequently. So over time, high activation energy synthetic reactions are not going to prevail. They occur less frequently than low activation energy hydrolyses and degradations. So this distribution, which you get in a fluctuating non-equilibrium system at steady state, is an anti-life distribution. And I've just put them side by side there. So the steady state anti-life distribution and the dynamical state pro-life distribution. And you can do various tests to compare them, compare the productivity of each of these fluctuating scenarios, the steady state and the dynamical oscillating state. So in this experiment, it's running simple linked metabolic cycles that were studied experimentally in 2018, where the input is pyruvate and glyoxylate and hydrogen peroxide. And with ammonium ions added at the right place, out pops aspartate. And we found that the relative productivity measured by the production of aspartate in the system run dynamically, so this right-hand system, is 20 to 220 times that of the steady state system. In this experiment, we've studied the formation of vesicles or micelles under a fluctuating oscillatory drive. And the input is a simple amphiphilic lipid species of some kind. And then we added in a small peptide to the input. So in the cell, we have simple, relatively unstable vesicles, just the amphiphilic lipid species dynamically forming micelles and then falling apart. So it's not very, these micelles are not very stable on their own. And an activated amphiphilic peptide, which forms peptide stabilized micelles. competing for the same lipid substrate. So we've got this simple, I call it a simple complex system, a competitive system. They're competing for the same substrate. One of the simplest sort of biotic things that happens is competition. And well, this is just a reaction schematic. The main thing to note is that we've got this competitive production of simple vesicles at low activation energy. And peptide, the competing peptides stabilize vesicles at relatively high activation energy. So all the models that we run computationally are thermally self-consistent. The temperature dependence of the reaction rate is built into the model. We have all the activation energies, pre-exponential factors. And the questions we asked of that simple complex system are: what is the effect of changing the variance of the input fluctuations? And what is the optimum variance of the input fluctuations such that net progress could be made towards the more complex peptide stabilized vesicle system? A little bit more towards life. A simple micelle system is not going to do it. Now, the variance is a measure of how violent the fluctuations are. Fluctuations which are too violent are more likely to tear the system apart than evolve it. Well, the results turned out to be quite dramatic and very interesting. Here we plotted the concentrations of simple vesicles up top and the more complex peptide vesicles for different values of the thermal input fluctuation variance. Don't take too much notice of the numbers, they're just scaled, dimensionless numbers. But a variance of 0 represents a completely smooth system, what people aim for in the lab, what the chemical engineers need economically. So for small fluctuations with a variance of less than about 0.4, the peptide vesicles remain nearly constant in concentration because high temperature fluctuations are rare. Okay, with a small fluctuation variance, the output temperature fluctuations in that spectrum, the high temperature synthetic reaction fluctuations are going to be rare. So production of active peptide is limiting, and the simple vesicles decline a bit because there is theft of the amphiphile by the competing peptide vesicle production. Then for intermediate values of the variance, the peptide vesicles increase sort of linearly, because there is increasing availability of the active peptide as high temperature fluctuations become more frequent at a slightly higher variance. The simple vesicles rise steeply to a maximum despite competing for the same amphiphile substrate. So the competition still allows simple vesicles to increase, but then the inevitable happens. The simple vesicles crash. They lose out in the competition as more frequent high temperature fluctuations predominate, allow the stable peptide vesicles to form faster and predominate. Okay, so I better, how long have I got left?
Well, you're 5 minutes into the discussion now, so.
Oh, okay, well, I better wrap it up. Well, no.
You've been speaking for 25 minutes.
Well, I better wrap it up.
The reason why I say that is
Well, anyway, I've nearly finished anyway. I'll just put up that fluctuating time series window again. And the results imply that overall that thermal stochasticity is beneficial for chemical evolution towards more complex systems. I was going to skip these bits about redundancy anyway. And in conclusion, we have the far from equilibrium requirement is a necessary but not sufficient condition for a stochastic environment to support protometabolism, biosynthesis, and chemical evolution, so non-enzymic processes. In addition to that condition, the medium is required to sustain non-steady or dynamical activity that can produce that right-weighted pro-life distribution of output thermal fluctuations. And finally, fluctuations ain't fluctuations. Some fluctuations are better or worse than others at fostering complexity. And finally, the messiness of nature also may be a necessary condition for complex prebiotic systems to emerge and persist. So thank you very much.